Hi. So for the change of pace, I'll be using English. So, hi, I'd like to introduce our paper, Forecasting the Physical Fitness and All-Case Mortality Based of School Children's Fitness Measurements. Wow, that's a handful. So this is part of a Crowd Health AU project in the Horizon 2020 from 2017 to 2020, integrating high volumes of health-related heterogeneous data from multiple sources with the aim of supporting policy making. It's basically a drive to take the patient records and make them more holistic, basically have all the data in the same place in the same manner so that it can be cross-referenced in use. There are 5 use cases in the project: Germany, Greece, Slovenia, Spain, Sweden, United Kingdom, and partners from Taipei. So the SLOFIT dataset from Slovenia, if anybody is asking, is the national surveillance of physical and motor development of children and youth in Slovenia. So probably everybody here had the fitness test during their school years where they tortured you, made you measure height with pull-ups and so on. So these are the motoric tests, height, weight, and triceps skin fold, basically the measurement of fat in the body. So motivation. There's a clear link between obesity, low physical fitness, and health problems, right? We want to use a SLOFIT database to forecast the risk for children and provide a tool for policymakers so that they can improve physical fitness of school children and therefore the physical fitness and longevity of adults. The idea behind it is that the data is taken from an individual at age 6 and onward. That data is used to forecast the physical fitness, BMI, and so on at age of 18. And then this data is used to assess the health risks for the individual based on his statistics. Now, the purpose of this is that a policymaker sees the general state of his reign, let's say that, a kingdom he's looking at, provides possible interventions that are already in the system, let's say an additional hour of fitness education for children, and sees if that and in how much and in what regard it improves the fitness of the adults, and sees how they will respond to that. So now to the more technical bit of the discussion. In the crowd health system, the data is stored in FHIR, written as F-H-I-R, red FHIR. It's an international standard from HL7. It's apparently next generation for storing health records. It is a NoSQL, I think, but I'm not completely sure. The specification is free to use without restrictions, so that it's human readable. It should be human. So if we're looking at how our part, the purplish bit, connects to the rest of the crowd health platform, we have the LeanX scale, which is a NoSQL database. That's basically the center of all the systems around it. The front end and the PDT call all the systems, provide the calls to visualization, and our bit in Django creates the forecasts, aggregates the data, has a bit of catching done there to speed up the system, and so on. The forecasting. Python with Django, Unchained. REST interfaces for forecasting, aggregation, risk assessment, and causal analysis. And as I said before, SQL, a small database to catch the data so that the system works faster because the queries to the database can be quite long. The integration to the LeanX scale. So Linux scale is, as I said, a database. All the analyses that are stored that are made are stored in the database, and they call, when the analysis tool is called, it registers a job, makes the analysis, stores the result, and marks job as finished. And this is for the whole system. So all the tools, all the analysis for different parts of the system have the same workflow and store the data in the same manner, which makes it easier to integrate, and it's actually quite automated to make REST calls from the Linux call, PCDB, to the analysis tool in the same manner by filling out forms. The forecasting is done in Python with skitlearn, I think. It's a machine learning library, enables powerful machine learning. The job of it is to generate models from data, store the data into our local database, and generate predictions based on these models. So these are the models that predict the measurements, let's say, of the adults after they are out of school. So our forecasting accuracy is decent-ish. At this time, linear regression was found to provide the best results. We are working on better models, and hopefully we'll have something quite soon. For instance, so this is Teja. Weight is apparently a lot better than height, which makes no sense to me, but fine. And finally, the risk assessment is based on literature. We have the information that, for instance, if you have a BMI of 22.5 to 25, this is the reference, this is the normal risk. And if you are under that, you're in more health risks because you're underweight. And if you increase your weight to unimaginable proportions, you are in much higher risks. The same is for cardiorespiratory fitness, CRF, which we model by using a 600-meter run. And the better you are, the less your health risks are in the future. So this is based on quintils, and muscular fitness modeled by sit-ups done in 60 seconds is also from the literature. We estimate that these are the increase in risks if you have low fitness. So obviously, now just to end up, I'm the poster child for health, as you can see, Matej Cigale. And recap, we're developing a platform that enables informed decision-making for policymakers, focusing on yearly assessment of school children done in Slovenia. And we have powerful machine learning that enables the prediction of health in adults. Questions? Yeah.
If you go back to the graphs,
sure.
the error rate increases specific ages.
Yeah.
Well, I mean, is that a problem because
the problem is that, children grow at different rates, and you have a growth spur in adolescence, in early adolescence, and puberty, let's say, and that we can't really predict when that will happen. Because each person will go into puberty at a different time, and will start growing very suddenly, and his height will increase quite a lot. And so there's a large error rate in that regard.
You're predicting the height at 18 or at each age?
So I think we're predicting the height at 18 based on this data, based on this age, data of this age. So
the data at 13 is not, if you use the data at 13, it's
Yeah, apparently. I mean, I'm not doing the predictions, so perhaps not the best person here. But yeah, that's how I understand it. If you have that much data, I mean, children at age 6, they are a different height, but the difference is apparently you skyrocket and some people start growing faster than others, and then the prediction value is harder, apparently.
I don't know if you know that, but do you use also the data from past? So basically, how was the growth from, I don't know, 6 to 10? And
Yeah, I mean, so, oh, sorry. He's asking, do we have the data? I mean, what we have is, what kind of data we're using for making the predictions, right?
Yeah.
Okay, so what we have for the growth is height at 6, height at 7, height at 8, height at 9, height at 10, height at 11, height at 12, and so on, till 18, luckily. And we're trying to predict the height at 18. Now, as I said, this was actually done before I was even on the project. But apparently, it's easier to predict the height if you have just the beginning of the age, the first few years, than later on. Yeah, it's the growth spur is problematic. It makes a mess of the models. It's going to be the different models will solve that. That's the idea right now. Data science. Any other questions? Yeah.
So maybe you don't know that because you said you didn't do the machine learning, but
yeah.
Are the measurements made for specific ages, or are they made for specific school years? Because people can be over a year of age difference in a specific.
Yeah, that's one of the problems. So the data we have is the birth of a person and when the measurement was taken. So you have the exact age of the individual.
Mm-hmm.
I'm not doing it. I might be doing it later on. I feel that the more important would be the month at measurement, because that would give you a lesser problem to predict. Because if you measure someone at age 6, he can be 6 years and 11 months and, let's say, 30 days. Or he can be just 6 years and 1 day. So yeah, there's a large difference there. We're not taking care of this now, but yeah, it should be a parameter in the machine learning. Yeah?
Another question?
Sure.
So what does it mean error 40%? So it's really strange because you can't miss by 40%. Repeat the question.
What does it mean for the error to be 40%? You got me here as well, actually. I don't know what the prediction error number is, but it's probably means that the prediction is somehow offset by the height, right? If you predict the error by centimeters, maybe? I don't know. Sorry. Sorry? No, that's way too good. I don't know. I think it's sort of an error rate based with offsets. Like if you have a bigger error in height, you have a bigger error measurement.
By the way, the literature says that at age about 1, maybe 2 years, you can predict the height of a person, grown-up adult, by a couple of centimeters. So that's
Yeah, I think it might be if you have the information about his parents, mind you.
Yeah.
We don't have that. We don't have that. We can't use the information about the parents. We could maybe recreate that, but it shouldn't be done.
Why not? I mean, this is the best way.
It is. Even better is you take a gene sample and you can give it an accurate measurement.
A couple of €100. Getting information about parents is okay.
Yeah, probably. I mean, on the other hand, I'm taller than both of my parents. Well, both of my theoretical parents. So it might be bad. You do know that 1 in 10 people, his father isn't who he thinks he is.
Mother is probably
Yeah, mother is like this tall, my father is like this tall. I'm taller than both of them. So genetics.
and the reason there because of this growing up. So
Growth spur, yeah.
That's I think is pretty well known.
Yeah, I
Some
mean,
people grow sooner, some people grow
Yeah.
later, and it's the reason.
no, what we are trying to do is predict if the growth spur has already happened or it will happen. The problem, an interesting problem, is that in the literature it says that the growth spur is pretty pronounced, right? But our data says that it's not all that pronounced as the literature makes it seem to be. Because some children apparently just grow linearly for the whole 10 years.
So obviously this method is not very good. We should
Yeah.
to the existing methods.
Yes, exactly.
Any further questions? No? Thank you very much. Riposta in the cocktail. Possibly. This is the speaker's new